Hello everyone, my name is Dylan Vo, and today I will be presenting to you a study titled Adversarial Sensor Attack and LiDAR-based Perception in Autonomous Driving. I would first like to start by acknowledging the researchers involved in this study and those who authored this paper, as well as Michigan State and UCI for providing the funding to support these alumni. In this overview, I have listed the layout of this presentation. I will first start with the problem statement, where I'll state the problem that we are attempting to solve through this study. I'll then follow with the background while explain what laser detection and ranging, or LiDAR, is, and how LiDAR attacks work. I will then go through each of these topics discussed in the paper. Then, I'll end with a discussion of these topics, including how autonomous vehicles can use this knowledge to defend against attacks, and finally, I'll conclude with what we learned. To understand the objective of the study, a problem statement was created as a guide. The problem statement I came up with is, in contrast to prior work that focuses on the security of camera-based perception, the security of LiDAR-based perception for autonomous vehicles is a highly unexplored topic that we would like to understand better. To understand the developments made in the study, you would first need to understand the background of this field of research. Traditionally, autonomous vehicles have relied on sensors for localizing their environments as well as perception. Typically, these sensors include LiDAR, cameras, GPS and IMU, and other major sensors. Laser detection and ranging, or LiDAR sensors, will be the focus of this presentation. The most important feature of LiDAR sensors is that they can easily capture distance data in a 360-degree range surrounding the sensor. LiDAR sensors work by emitting IR light pulses in a circular pattern around the sensor. These IR pulses are reflected back to a receiver in the sensor that tracks the time it took for the pulse to be sent back to the sensor. By knowing the time between emitting the pulse and then receiving it, we can calculate the distance that was detected using the known speed of light. This is known as time of flight ranging. Knowing the working principle of a LiDAR sensor, how would a LiDAR attack work? Well, attackers can exploit this working principle by emitting external IR pulses to a victim LiDAR system, creating spoofed measurements. By doing this, attackers can attempt to create spoofed obstacles in the machine learning detection software integrated into the autonomous vehicle. I've included a visualization of how LiDAR sensors are used in autonomous vehicles for detection. As you can see in step 1, the LiDAR system is transmitting IR pulses in a 360-degree range surrounding the vehicle. In step 2, we see that the IR light has bounced off another vehicle. In step 3, this light is received by the LiDAR receiver, allowing the vehicle to calculate the distance between the two objects with the known speed of light. An attack goal and threat model were created to guide the research in this study. The study established that the goal of an attacker would be to fool LiDAR-based perception in autonomous vehicles into perceiving fake obstacles. The model that this attack would follow is through spoofed LiDAR perception by shooting malicious laser pulses at a victim autonomous vehicle. This would be done by shooting pulses from an attack vehicle while close to the victim vehicle. As you can see in the threat model shown, the attacker would attempt to inject fake data through these malicious laser pulses, fooling the machine learning model into predicting an obstacle that didn't truly exist. Blind sensor spoofing is the process of attempting to spoof a LiDAR system by randomly transmitting IR pulses to the victim LiDAR system at an attempt at spoofing an obstacle. In previous research, spoofing attack experiments have used a photodiode, delay component, and an IR laser to sync with the LiDAR sensor and transmit malicious IR pulses. The Shin experiment has a few limitations, including only a 100 microsecond fire rate, restrictions to only fire in a horizontal line, and only being able to spoof 10 fake dots. In this experiment, the apparatus was improved in every way, allowing the researchers to spoof 100 fake dots. As you can see in the illustration, the experiments work by using a photodiode as a trigger for a delay component that then triggers an IR laser to transmit malicious pulses to the victim LiDAR system. The picture to the left depicts fake dots detected by the LiDAR system that were recognized in a 3D point cloud. While these dots may be detected, it does not necessarily mean the autonomous vehicle will treat this as an obstacle, because this data must first be processed through a machine learning model that will predict whether this spoof data is an obstacle. On the right, we can see the deterministic pattern of the LiDAR system used in this experiment. Because the LiDAR always follows the same sequence, an attacker knowing this information can easily send pulses at specific time steps to generate a spoofed obstacle. Knowing the details discussed previously, the researchers established a problem of generating spoofed obstacles as an optimization problem. They attempted to use optimization to fool the machine learning model at the input level, as they found that perturbations to a specific input would have the most success at spoofing. Some of the technical challenges of this method include that attackers have limited capability of perturbing the machine learning model inputs, especially if this knowledge is not known. Optimization methods used in previous studies do not work for this case for the same reason. And finally, successfully changing the output of the machine learning model does not necessarily mean successfully spoofing an obstacle. Here's how the researchers generated adversarial examples through optimization. Though they found that, although they were able to spoof 100 fake dots, only 60 could reliably be done in each experiment. Because of this, they treated 60 dots as a maximum, with 20 and 40 being used as test cases. The experiment saw that the attacker could modify the distance, altitude, and azimuth of a spoofed dot by changing the delay of the attacker laser pulse. As you can see in the picture, the distance can be adjusted by changing the delay of the pulse, altitude by changing delay and interval of 2.304 microseconds, azimuth by changing delay and interval of 55.296 microseconds. Here's how adversarial examples were generated in this experiment. Firstly, a function for adversarial loss was designed. The researchers then attempted to optimize attacks by minimizing this loss. The images show this process of generating spoofed obstacles in the 3D point cloud. The image to the left shows the process of minimizing the adversarial loss function with two different step sizes. We see that a larger step size causes the function to miss the absolute minimum more easily. On the right, we see the relationship between the number of spoof points and the success rate. Throughout all cases, sampling-based optimization was always better than vanilla optimization. Notice also that there is a huge jump in success rates between 40 fake dots and 60, where it goes from around 30% with 40 fake dots to around 75% success with 60. In this experiment, LiDAR sensors were attacked by an attacker attempting to spoof obstacles 2 to 8 meters to the front of the victim autonomous vehicle. The 3D point cloud frames were collected as data. A subset of 300 3D point cloud frames were uniformly collected from this data, and analysis was done. In the graph, we see that overall, a test with 60 fake dots has the highest attacker success. For all fake dot counts, we see that the more 3D point cloud frame index differences there were, the lower the success rate of the attack. A driving decision case study was performed to attack a simulation that generates driving decisions based on real-world sensor data. The case study was focused on two attack scenarios, the first being an emergency brake attack where the attacker would force the autonomous vehicle to trigger a stop decision by spoofing an obstacle in front of it, causing the vehicle to stop when there is no real obstacle. The second scenario is an autonomous vehicle freezing attack where the attacker spoofs an obstacle in front of the autonomous vehicle while it is waiting at a red light. This causes it to be stuck in this light forever. The images show demonstrations of what these attacks look like. I would like to wrap this presentation up with a discussion of some limitations of this experiment. Firstly, this study is limited by how the experiments were performed. A true real-world experiment would be to dynamically aim at a LiDAR sensor on an autonomous vehicle while an attacker is moving in an attacker vehicle. An experiment like this could be performed in the future. Another limitation was in how the adversarial examples were generated. Because only analysis was done with a specific threat model targeting the machine learning model, the research done here does not capture the entire potential of LiDAR attacks. This study also only did analysis on perception and can be improved to target specific abnormal autonomous vehicle driving decisions outside of ones based on perception alone. How can autonomous vehicles with LiDAR systems defend against attacks? One issue with LiDAR on autonomous vehicles is that they typically map the 3D point cloud generated by the LiDAR into 2D matrix, causing it to lose height information. By avoiding this conversion into 2D, the autonomous vehicle can become more aware of changes in the height axis, making it more robust. Another potential resolution could be sensor fusion, or using a method of combining data from multiple sensors to detect anomalies. Having multiple sensors makes it more difficult for attackers because this would mean attacking multiple sensors simultaneously. The downside, however, is that all sensors must be functional in order for this to properly work. We can also mitigate attacks by modifying the internal structure of LiDAR sensors to reduce receiving angles and filter unwanted light. This would make it more difficult for attackers to accurately spoof pulses at the cost of limiting the range and sensitivity of the sensors. Finally, we can randomize how the LiDAR fires laser pulses. We saw earlier in the presentation that the LiDAR follows a sequence that can easily be followed if the attacker has knowledge of the sequence. Randomizing the sequence will make it impossible for an attacker to sync with the system. To summarize what we learned in this presentation, we saw that this is the first security study of LiDAR-based perception for autonomous vehicles. The study reproduced a LiDAR spoofing attack and saw that blindly spoofing dots won't work because doing so wouldn't trick the machine learning-based object detection process. An attack was formulated by optimizing an adversarial attack on the machine learning model input. An experiment that improved upon a previous experiment was used to analyze how well an attacker could spoof obstacles in a stationary LiDAR system. This led to a success rate of around 75%. The researchers then performed a case study in which 2 attack scenarios were tested, which led to successful attacks. Finally, we discussed how we can defend against attacks in LiDAR-based autonomous vehicles at the system, sensor, and machine learning model levels.